Good day for everyone. We are Manuela Lopez Leon and Maria Paz Galindo, and we are going to present you our practice 1, which name is hydrogen bonding, hydrophilic and hydrophobic interactions. In first instance, we are going to make a brief introduction, starting with what is a molecular dynamics. Basically, it stands as a computational simulation method enabling the analysis of molecular interactions at an atomic level, facilitating the study of time-dependent evolution of molecular systems. This approach involves calculating the interatomic forces using Newton's law of motion, and through this technique, it becomes feasible to compute various physicochemical properties such as solubility, pressure, entropy, viscosity, free energy, and phase transition points. Now we are going to talk about GROMACS, that it is a widely employed tool for conducting molecular dynamics since it is a versatile instrument, enabling simulations of systems with a high number of molecules, such as proteins, lipids, and nucleic acids, while primarily geared towards molecules with intricate bonded interactions. GROMACS is esteemed for its efficiency in calculating non-bonded interactions. Continuing with the objective of this practice, it is basically to assess the impact of temperature on water viscosity through a molecular dynamic simulation using GROMACS.
Methodology consists of four phases: minimization, heating, equilibration, and production. Minimization: the simulation could fail due to the very high potential energy between two atoms, that can create very large forces and interactions. Thus, the potential energy must be analyzed and minimized. Heating: the molecules undergo an increase in temperature as kinetic energy is added. Changes of position and increase in speed are presented. Equilibration: the system is brought to equilibrium, the molecules are allowed to move freely. Analysis of potential energy, kinetic, and temperature. Production: the system is in equilibrium and data on the molecules of interest are collected. Analysis of potential energy, kinetics, temperature, and forces of molecular interaction.
Once the molecular dynamic simulation was run, the first relevant results were the viscosity values obtained for each temperature. In this case, we can observe four viscosity data points per temperature, from which an average was derived. These average were then plotted as shown in the graph on the right. In it, we can observe that as the temperature increases, the viscosity decreases. Continuing with the results from the heating phase, we plotted the data from the three temperatures on a single graph. In the case of kinetic and potential energy, we can observe that in the three scenarios of the temperatures, they increase over the elapsed time. Additionally, it is noteworthy that the highest energy levels from both cases consistently occur at the temperature of 363 Kelvin, and the lowest energy points are in 303 Kelvin. In this case, the temperature during the heating stage exhibits the same behavior as the kinetic and potential energy graphs that we saw before. For the calibration phase, the obtained data from the three simulated temperatures were once again plotted on a single graph for each type of energy, where we can observe that the resulting graph for kinetic and potential energy, where the highest energies occur at the temperatures of 363 Kelvin and the lowest occurs at 303 Kelvin in both cases. In this case, the temperature during the calibration stage exhibits the same behavior as the kinetic and potential energy graphs that we saw in the last slide. Continuing with the results from the production phase, we can observe how the behavior of the kinetic and potential energy of the molecules varies as they move freely. Peaks are evident at all three temperatures in both graphs, and it is worth to mention that the highest energy belongs to the 363 Kelvin temperature, while the lowest energy pertains to the 303 Kelvin temperature in both graphs. In the temperature and total energy graphs, a peak-like behavior similar to what was observed in the previous slide is evident, and also the charts follow the same temperature trends. The Lennard-Jones energy is depicted in the graph on the left, and it can be observed that the energy of apolar interactions is higher at the lowest temperature and lower at the highest temperature. On the other hand, on the right, we have the Coulomb energy, where it's evident that there is greater energy in polar interactions at a temperature of 363 Kelvin and lower at 303 Kelvin.
We determined the following: viscosity decreases as temperature increases, because the kinetic energy of the particles increases, making their movement freer and the distances between the molecules larger, which decreases molecular interactions such as van der Waals forces and hydrogen bonds, and that cause the fluid to be less viscous. In the production phase, we can see that due to the heating phase, the molecules are charged as they enter to the production phase. In this phase, the data presents a random dispersion because of the movement and collision between the particles. When analyzing the kinetic energy, it is determined that when it's passing through the heating phase, it increases due to the increase in temperature. In the equilibrium phase, there is also an increase, but to a lesser extent. There is no significant change in production. In the graphs of potential energy, we can see a similar behavior. In conclusion, we were able to achieve the objective of assessing the impact of temperature on water viscosity through a molecular dynamics simulation using GROMACS. Additionally, we determined that as temperature increases, viscosity decreases. Because of molecules being to move faster, our intermolecular forces decrease, which causes the particles to move more easily. The temperature influences the kinetic energy and therefore increases the molecular speed. They have a directly proportional behavior. And the potential energy and the interaction of molecules have an inversely proportional behavior.